So my name is Peijs. I'm from the University of Warwick. I'm the professor in polymer engineering. I'll be chairing this session. And we probably better straight start off with the first speaker, who is going to be Helen Jordan from the British Plastic Federation. And she's going to tell us about the sort of state of the union of plastics in the UK, I guess. You know,
yeah, lovely. I'll stand here, so hopefully I'm picked up on the mic. So good morning, everyone. Yeah, I'm Helen Jordan. I'm the Sustainability Manager at the British Plastics Federation. So we're obviously covering today infrastructure requirements for the future. And what I wanted to do to discuss that really was to talk about a new report that we've got coming out next month. So that's how I'm going to sort of address the infrastructure requirements this morning. So this report, it's the BPF Recycling Roadmap. It's in its second edition, which is to say it's coming out next month. You may or may not know that in 2021 we brought out a recycling roadmap, and that was looking at, that was looking at sort of where we are now as the industry. So where are we in terms of, across not just packaging, across all the sectors that plastics use, where are we in terms of what's placed in the market, where are we in terms of what goes into the plastic waste stream, and where are we in terms of recycling. And then we took that information and then we looked at, okay, what would we like to achieve? What could we achieve by 2030? And we forecasted for that. And then we looked at what needed to happen in order to achieve that forecast. So what this is doing is it's updating that report. So it's going back and updating all the where we are now data. We're going to look at some wider sectors. We've introduced agriculture this time. We've introduced household, leisure and sports, which we hadn't before. We've widened our look at construction and demolition. And we've widened our look at the medical sector as well, so focusing more on sort of the wider NHS than we did previously. We're also looking at environmental impact as well, so we're looking at the environmental impact of the plastic waste as it is at the moment. And then we're going back to the forecast again. So we went back to the 2030 forecast and saw, okay, what do we now think we can achieve by 2030? When we originally wrote it, we were 10 years off 2030. We're now just over 5 years off it. You know, what we wanted to achieve by that point isn't going to be possible now because we haven't had the changes that we wanted to see from the first roadmap. We've had delays to EU legislation. We haven't had that investment into the infrastructure that we needed to have in order to achieve the 2030 forecast as it was. So we've updated it on what we now think we could achieve. Still, we've got 5 years. We could achieve a lot in 5 years. And we're looking forward to 2035 to say, well, what could we achieve at that point? And we've had to take into account, obviously, assumptions in order to do that and key changes. And apologies, we've missed the G off the end of recycling. That's my that's not the real front cover, that's my version of a front cover because it's still with the designers at the moment, so it's lost a G somewhere along the lines there, so apologies about that. So I will say the recycling roadmap, we've produced it with Recoup. They've worked on it for us, putting together the data and working with us on developing that forecast as well. So this is some of the information that's actually in there. I wanted to bring this out, obviously, because we're talking about infrastructure this morning. And it's good to kind of reflect on, well, what do we have already in terms of infrastructure and capacity for recycling to see what we need to have going forward. So we've got just under 500 kilotons of mechanical capacity for the household stream and just over for the commercial packaging streams. We've got about 120 to 140 kilotons of capacity in the end-of-life vehicles and waste electrical electronic equipment. And then we've got about 21 kilotons of chemical recycling capacity being commissioned and coming online at the moment. So we're getting to about 1.1 million tonnes of capacity that's in the UK at the moment. It's really hard, I will say, with all this data in the recycling roadmap, it's really hard to get really good data. And I'm sure that's a problem that a lot of you have found as well. So we have used expert opinion, expert views to try and put together some estimates where we couldn't get actual data. But that's where we feel we are for capacity at the moment. The main thing I wanted to show you, though, was sort of forecasting through what we want to be able to achieve going forward. Now, you will notice there are no numbers, and that is, I did do it on purpose. Obviously, the report isn't coming out until next month. I didn't want to give too much away today, but I wanted to talk you through sort of what's going up and what's going down, really, in terms of the forecast, but without sort of giving away the whole report at this point. So, I'm going to move this way and hope you can still hear me. So in terms of, this is 2020 and 2022 data. That's actual data that Recoup's put together for us here. And what I'll do is I'll compare sort of going forward to the 2022 data as it is there. And we've got both the 2030 and the 2035 forecast up there. So hopefully you can see the different colours there, but the dark blue is our mechanical recycling, And in terms of mechanical recycling, we're wanting to see pretty much double the amount of mechanical recycling happening between 2022 and 2035. So huge, that's going to be a huge amount of investment, a huge amount of growth in the amount of infrastructure in the UK. But we see that as really important in terms of keeping our material here and using that sort of existing already understood technology to drive forward our recycling. So massive growth in mechanical recycling. It's about 1.3 million tonnes more of mechanical recycling capacity we're going to need in order to achieve this forecast. So that's going to cost, 1.5 billion pounds in order to put that capacity in place. So working from the bottom up, we've then got export to recycling. So we want to see a big reduction in the amount of export taking place. We don't want export to be a route for low quality material. So we want to have that also for high quality material to generally drive up the quality of material. So less export taking place. Moving on to chemical recycling. Now, the big thing here really, if you're comparing it to what we were thinking last time in the last forecast, we've got a lot less chemical recycling capacity going on stream by 2030 than we were hoping for when we did our original forecast. And that's because at that point when I spoke to a lot of the chemical recycling companies, what they were wanting to deliver by 2030, a lot of them have not delivered on what they were going to do. There's been lots of issues in terms of getting approval for mass balance in the UK, lots of other issues around sort of making that investment into the UK. So there isn't going to be, we don't feel there can be the capacity, the amount of chemical recycling capacity that we were hoping for by 2030. So that is considerably less than we were thinking about before. So it's about 100,000 tonnes by 2030, but we can see by 2035 that we've got that decade, we can deliver a lot more. So we want to be getting up more to the source of sort of 400,000 tonnes worth of capacity for chemical recycling. So we think that can be achieved, but we've got to make those changes as with all these things now in order to do that. Compost, AD and other, we've allowed other in that category as well, because we can see that we're talking 10 years into the future. There's new innovation happening all the time. We want to encourage that innovation. So we wanted to allow for the fact that there's technologies developing, enzyme recycling, for example, taking place. So that's to allow for that, and obviously composting and AD, where it's appropriate, I think is the key message there, making sure that you're using it in appropriate uses, not where it's going to get into the recycling streams. Reuse, we didn't talk about reuse in our last roadmap actually, but we can see with the plastic packaging waste regulations coming into Europe, there's going to be pull through into the UK of more reuse taking place. So we want to see that happening. We want to see how we can help in terms of delivering that infrastructure. So we're getting up to about 10-13% of reuse of material going into the reuse streams by 2030 and 2035. Energy from waste is decreasing, and the reason for that is we can see that, well, we want to encourage more recycling, but also plastics going into energy from waste facilities. There's a high calorific value to that. You've then got the issues around those companies being able to achieve their net zero targets. So waste management companies are looking at how to divert plastic out of their energy from waste streams. So we can see how that will continue to develop. So we're reflecting that in the forecast and having less material going to energy from waste. And that's the same as we had in the previous forecast, I will say. Landfill, we've got slightly more landfill actually than we had previously. So a big reduction still. I think it goes from about 22% down to about 6% of material going to landfill. We were, in our previous roadmap, we were putting that right down to 1%. And the reason we've changed that is we've put together as the BPF a plastic waste hierarchy. And actually we've grouped energy from waste and landfill into the same level. And the reason we've done that is to consider the sort of the carbon impact of energy from waste, but also there's other sort of considerations in terms of the impacts of different disposal routes. So what we wanted to do is people to be considering what's best for their particular material. So we didn't want to just sort of be showing this to be driving all material out of landfill, because we can see in some applications actually it would be better to send those material to landfill than energy from waste. So that's what we're reflecting in that. And then we've got a sort of other category as well for sort of other general waste disposal routes. So as I said, we've got about 1.3 million tonnes of mechanical recycling capacity being needed. We're going to need nearly 400,000 tonnes of chemical recycling capacity going in order to achieve this forecast. So we need a massive investment and definitely massive growth in the amount of infrastructure in the UK. And that's not going to happen magically. We can see that that is going to need a lot of really fundamental shifts in how people are behaving and how legislation interacts with us, and in terms of giving people the confidence to make those investments. So we've got 16 key changes that we're going to be setting out in this report, and we'll be putting those into government and saying to them, this is what we need to see. And they're around 3 areas. They're around increasing investment. So one thing that we have talked about a lot at the BPF is the money from the plastic packaging tax. Why can't that go into investing in recycling infrastructure and to developing the sector? So that's one of the messages under that area, along with others. Optimising legislation, existing systems. We're all very well aware of all the delays to legislation. We need to get that legislation delivered. We need to have a legislation package that is supporting the industry growing. And then we've also got a stream with changes around improving communications and collection systems. So one of those areas is around looking at beyond curbside collection. What do we need to happen in order to drive more take-back schemes and to drive more collections on household waste and recycling centres? So kind of moving beyond just the sort of standard items that we're seeing collected from the curbside through simpler recycling. So that's the sort of key areas around the changes. As I said, it's coming out next month, so please look out for that. If anyone wants to particularly receive a copy, please come and talk to me, and I'm happy to do that. But that's sort of our take on where we're heading, or where we want to be heading as an industry, and the infrastructure requirements to achieve that. Thank you.
No, sorry, no, after you.
No, you go.
I'll come as well, okay. Double act.
Yes, no. So our next speaker is from Barry, Circular Polymers. I was actually at your site on Tuesday.
You were, yes.
Very impressed. Very clean, I have to say.
Thank you.
Very noisy though. But so I'm sure. Well, you're going to tell about this fantastic facility in Leamington.
Yep. No, wonderful. Thanks everyone for the opportunity to talk to you. Pleasure to speak in front of you here this morning. I'm delighted to be able to talk to you today about what we believe at Berry to be the future of contact-sensitive, mechanically recycled polypropylene. Now, as part of Berry, we have an ambition to be able to offer these 5 different options to all of our customers. One of the main areas of focus, which we're going to be talking about today, is recycled plastic. Now, as a business, polypropylene is one of our main substrates that we make packaging with, and what we found about 5 or 10 years back was that actually there was very limited amount of good quality recycled material to enable us to turn packaging back into packaging. So what Berry decided to do to support the much needed infrastructure that the plastics recycling industry in the UK requires is they developed, out of their own money, $30 million worth of investment into a state-of-the-art facility in Leamington Spa in the UK. So this proudly introduces our proprietary CleanStream technology, which is one of the first closed-loop systems that can mechanically recycle domestically recovered household waste back into packaging that is then suitable to be recycled at the curbside to then go back into our facility to be recycled again. Now, this particular concept was born of 6 key areas. And this kind of explains a bit about what it is that we did with this facility. So these are what the marketplace told us 5 years ago was required of our particular facility. So we needed to have feedstocks available that had good, consistent qualities, which is why we chose household collected waste. Because even though across the UK, sadly, the way that recycling is done and the collection schemes aren't all aligned, but what the people in the UK do generally put in their household bins that are polypropylene are fairly consistent. As you will have seen when you visited the facility, a lot of confectionery tubs, butter tubs, yogurts and pot noodles, which is essentially what people consume in the UK. So consistent feedstocks, plus the ability for us to be able to have reliable availability so the UK collects on a widely basis. As we saw from what Helen was saying there, hopefully the increase in recycling rates is going to mean more feedstock becomes available. What we needed to have was product that could have good aesthetics. So generally recycled material from polypropylene often ends up being kind of downgrade to lower quality products such as maybe paint containers, industrial uses, which is fine, it's being recycled, but what it's not doing is going back into high grade packaging that can become itself again. We wanted to have something that had no odor, so we needed to have a facility that could decontaminate the material. And of course, we wanted something that could hopefully achieve food contact approval, which I'll detail a little bit later on there about how our progress is there. And we needed to have something that had lower CO2 footprint versus virgin material and that could compete with other types of recycling systems. Now I have a video here. It's about 3 minutes long, but I will cut it because it's quite long. It will take up all of my section here. But it has just some detail and some stats that I'll revisit as well, just about what this facility is able to offer. Okay, at that point I'll cut it short because it just continues to reel some of the information there. But as you can see, this particular facility is state of the art. Now this graph here demonstrates, this image here demonstrates what generally happens with polypropylene recycling that's put in the household bins. So as on the top there, it will often go to waste management sorting facilities, MRFs and PERFs. It is washed, it's recycled, it's converted, often into, as I said there, kind of more low impact and low performance products and things. Not to say that, a plant pot, a paint container, the wheel arch liner of a Nissan Leaf isn't a high performance product, but what you will never generally find is that particular product being able to be recycled back into that product again. So by having a facility that through multi-layer sorting and an AI-based sorting system that can determine whether the piece of packaging is food or non-food in its previous life, we're able to achieve a successful sorting rate that enables us to hopefully achieve full food contact food approval. We then have an intensive wash facility, 85 degrees for 8 minutes with a decontamination process following that. And because we have a lab on site, we're able to test every single batch for a full 24 hours to ensure that every batch we produce is able to be certified with a certificate of analysis that we send out to our customers to make sure that they're happy with the materials themselves. Because we're able to produce product that can be widely recycled back into household bins, it's a feedstock back into here. Now, just a stat that I really like pointing out, that particular video there mentioned that we take 40% of the available collected household polypropylene in the UK. So assuming all of you are very good recyclers at home, if you put your polypropylene back into your home recycling bin, there is a 4 in 10 chance that it will end up in our facility based on the recycling data that Recoup and Valcap provided for us. So real good chance at circularity there for this particular product. So our lab, we were able to offer GCMS, GCFID, NIAS, migration-specific testing, so all of the things that you would expect a full analytical, wet and chemistry lab to be able to offer. This particular lab is able to then ensure that we have no odour or good aesthetics, and then we are currently compliant with FDA standards. So what that means is that that is generally assumed that when you have an FDA letter of non-objection, you're able to then put products onto the market for beauty and personal care. We are chasing the EFSA, Novel Technology Food Contact Full Safety, and best estimates, if I'm being optimistic, Q1 next year is when we hope to achieve full contact food approval. Now, we used to have a recycling facility in Wimbledon, Plasground business, some of you may be aware of. This is what we were able to achieve previously through the fairly standard quality recycling process that we had. The key difference here between traditional recycling streams like our previous facility and CleanStream is the ability to achieve minimum 99% PP contact in that particular substrate. The higher quality yields you have, the less PE in the stream, means you're going to achieve higher PCR inclusion rates, no stiffness compromised, and actually a full high-class product that can be used for a whole wide range of suitabilities. This is the material that we produce. This is our affectionately called PP5, FDA MF20, or PP5 for short. So this is an ivory sort of coloured material, or Leamington white, as I'm trying to get trending, very Farrow and Ball. But for us, it's something which is really, really key here to be able to enable us to put product onto the market, as I say, to enable a second life for recycled polypropylene. Now, because we've had an assessment carried out by Qantas, we know that we have a 35% lower CO2 emission generation than virgin plastics, and this is only going to increase as we start to see energy efficiencies, the greening of the grid, plus our facility. We're hoping to expand with further solar panels, things like this. So because we know how much material we take in on an annual basis, we can very confidently state that we're able to remove 13,000 tonnes of CO2 per annum. And our ambition and hope is that this could be one of the first of many of these facilities, potentially in the UK, but certainly throughout Europe. So as I think I mentioned, we have at the moment US FDA letter of non-objection. Our ambition is to get EFSA and UK food standards approval beginning of next year, which will enable us to make full food contact material available, which would be a huge thing for us. So we're very well aware of and we're very aligned with the EU 2022-1616 recycled materials legislation. And the sort of applications that we can, from a technical standpoint, create are all of these here. So essentially, this material is able to be used right the way across the board of what Berry can offer, but just generally the types of packaging formats, it's something which is truly, truly phenomenal for us. And as I think I mentioned, one of the key things here, as we have a lab on site producing and testing every batch of material, we're able to provide a certificate of analysis in real time with every batch through to our sites that gives our customers the confidence to know that they're getting the highest quality material. And the last slide from me, just some examples of the products that we have on the market right now, which are beauty and personal care products that are made using CleanStream material. Our ambition, as I say, beginning of next year, is to start including full contact food approvals. So, yogurt pots, soup pots, confectionery tubs, things like this. So we believe this to be the future of mechanical recycled polypropylene. Done.
Okay, can you hear me okay? I have a video too. I just want to make sure that I can start and stop it. Yes, okay. So we're a mechanical recycler as well, like Berry, not quite as big, but I want to just explain our story. We have set up, why we're here today is because Innovate UK gave us a grant to build a plant in Peterlee for flexible plastics. And I just want to give you our story of what we've done to kind of establish our bona fides before we talk about the new plant and how we got to this point. So we were established in 2014 with a technology called BOSS. And the BOSS technology can separate plastics based on the density in a water tank. That's quite unique. Most mechanical recyclers are sorting material using near-infrared. And the problem with that really is that it's difficult then to sort black material. Because the near-infrared cameras can't identify black plastics. So we set up our first plant in Newcastle in 2017. We took in post-consumer waste, probably very like what Barry are taking in, Here's a picture of it here. So it's everything after all the valuable materials have been taken out, like PET bottles and PP bottles maybe, and HDPE bottles. And you can see, just looking at that waste, that about 1/3 of it is black. So if you can't identify 1/3 of the waste, then it's very difficult to get a pure plastic. And just for those in the room, the biggest thing about plastic is to get it to a high purity if you want to get it recycled. We probably all know that, but just for anybody else who may not. So our technology, what we do is we have a two-stage process. We shred and wash the plastic first, and then we put it through our BOSS technology rather than putting it through kind of near-infrared cameras. So just pictures of how we shred and wash it. Here you can see the shredding machine here. Then it passes through some magnets here, passes through a conveyor, and it's into a shred. Then it passes into a sink float tank. And in the sink float tank, we're separating the polyolefins from the sinking plastics. So the polyolefins being the PP and the PE, and the sinking plastics would be, let's see, HIPS, ABS, PET, PVC, anything that has a density greater than 1. The sink float tank will also take away any of the metals or any stone or any inert objects that are sinking. So just following the polyolefin content, we then shred that again down to 15 millimeters. Then we wash it in the tank on the right there that you can see. And then we send it into the BOSS system here. So I'm kind of speed dating you through what we do just so I can get to the flexible section. But this is then the BOSS section. The easiest way to understand it is really what we do is we feed the plastic in granules, like you can see shredded plastic, like cornflake size, into a water tank. We flush it to the bottom, like you would in a toilet. And in the middle, we have these plates with holes in them that are oscillating up and down. And those plates create whirlpools every time they oscillate up and down. And the best analogy I can give you is if you think of when you play that game Pooh Sticks, when you throw a stick into a stream, it'll accelerate quickly if you put in a light stick. But if there's a rock in the stream, there'll be a whirlpool behind that, and a little twig will just get stuck in the whirlpool, whereas a heavier branch will come down and just go straight through that whirlpool. So we have two different densities, PE and PP, and we're loading them into the tank with a stream of water that's pushing it down to the bottom, and we have these whirlpools that we generate in the middle that holds the PP, the lighter of the two plastics, and it allows the PE to go down to the bottom of the tank. Also, any other plastics that have been missed in the sink float tank will also go down to the bottom of the tank and sink. But the PE will rise back up because it naturally wants to float, whereas those other sinking plastics will sink. So what BOSS is doing really is it's separating the PP from the PE, but also importantly, it's getting rid of any PVC and any heavy plastics, which are really harmful if you want to recycle and want to make a pellet out of something when you have separated the other plastics. So it's quite agricultural, is what we've been told, which we took as a compliment. Well, maybe an insult at first, but then as a compliment, because we thought, right, it's sturdy and it works. Here's just inside the tank, the oscillation up and down. There's the plate that you can see, and this is just the back of the tank, the polypropylene coming out the back of the tank. And then it goes into a screw conveyor where we dry it, we dedust it. Here's one of the guys just taking a sample of the, just to show you the purity. And if I'd stop that at the right place, you can see how many particles are at the top and how many particles are at the bottom. We can get about 95% purity. So that was kind of 2017, 2018, 2019, probably still today if I'm honest, but it's still getting that process better and better and better. And then we came across, and so we produced bags of pure polypropylene and pure polyethylene. And I think then we went to sell that, and we had a huge problem. And that is a problem that's common throughout the whole of the recycling industry, which is not much talked about, but it's the melt flow rate or the melt flow index of the plastic. So because we were taking in mixed post-consumer material, that means we have mixed melt flow rate. And the melt flow rate, for those that don't know, and I didn't know when we invested all this money and set up this plant, is the rate at which the plastic flows when it's melted. So if you have different moulding methods, then you need different melt flow rates. So for example, if you're blow moulding a bottle, you need a melt flow rate of 0.5. If you're injection moulding a crate or a wheelie bin, you need a rate of 7. If you're making 1 million McDonald's toys, you might need a melt flow rate of 40. And you can think of it like miles per hour. There's a huge difference between driving at 0.5 miles per hour and driving at 40 miles per hour. So one is no good for the other. So when we would send our plastic out naively saying we got this 95% pure plastic to try and sell it, they'd say, what's the melt flow? And we'd say, well, on Excel, the average is about 2. And that was no good because in actuality, every flake had a different melt flow rate. And that's why you see plastic lumber in these products being the most common product that you mentioned in the previous file presentation. Because when that plastic comes out, if you can imagine, it's coming out of the moulding machine and it comes out slow at 0.5 mile an hour and then 40 miles an hour and it tears. And that's why you see your bench that you're sitting on in a park made from recycled plastic that's got this uneven surface. So what we had to do, we were storing our product for 18 months trying to find a solution, going to every conference, trying to talk to people. Everybody had the same problem. And we eventually came up with an additive that can deal with this problem, that can standardize the melt flow rate. And that was the key to really our next stage. So if you think of what we're doing, it was 2 stages. One was Boss separation. The second was solving the melt flow rate problem. So the melt flow rate problem allows us to make a pellet now by using an additive. It's a monomer additive, so it's a food grade approved additive. And it means we can now make, for example, these sealant gun cartridges, which have a melt flow rate of 7. And it'll take the color as well. And we can also, from the same material, then make these bottles that you can see here that are for shampoo bottles. So it's a blow molding process, and this requires a melt flow rate of 0.5. So it's a patented additive. It's a big breakthrough. It's little talked about in the industry, as I say, but it has allowed us then to create more plants. And this is actually something we're making for Berry. It's one of your 300-litre bins. You might recognize the plant. So all these different melt flow rates are possible from that mixed feedstock that you saw on the first shot. And that's something that normally, if you wanted to do this, that wouldn't be possible. It also allows us to recolor the plastic so that we can get different colors. I'll just play this on a bit. Not sure why it's, yeah. That allows us then to supply different colors. We can't get the white that you have, but we can get these kind of colors here up to the light gray that you can see in the screen. So how does it work quickly? Is if we want to make a bottle, we take a bottle grade, virgin plastic at 2% and add it into our 98% regrind. But that 2%, we've put our additive into that. That's the carrier for our additive, in the same way you'd have a carrier for color. And what our additive is like a magnet or a zeolite. Now it's plastic, but it acts like a magnet. So when it goes into the compounding chamber, which is metal, it gets sucked up to the chamber wall and forms like a sausage skin around our material. And the sausage skin is a good analogy because in the inside you've got lots of different melt flow rates, and then on the outside you have the melt flow rate that you want. So it processes like it has the melt flow rate of 0.5 for the bottle, but actually inside it is all these other melt flow rates. And then if we're making the sealant gun cartridge, we just change the carrier. Rather than having virgin bottle grade, we will move to virgin sealant gun cartridge grade of a melt flow rate of 7. And that then gets sucked up, and that's the sausage skin that's at the boundary layer. And that's what allowed us to make those products that you just saw on the screen, and also what allows us to recolor the plastic, because if we put in a master batch, that will get sucked up to the boundary layer as well. So that solved our problem of being able to sell it. It was easy to timestamp that because it was COVID, March 21, when we kind of first figured it out for ourselves, and then we started bringing it to market. It was COVID, so it was very slow. We did trials with companies like Berry and lots of other companies, and so we have a range of products now that we're able to sell. So they're consumer-grade products that have perfect surfaces and the right color. But it's taken us probably 3 or 4 years just to bring that to the market, and it applies for HDP, LDPE, and PP, and any of the other plastics that are out there. We built a second facility in Glasgow, then in the interim, which deals with medical waste, which is about 60% flexible material, 50 to 60% flexible material, 30 or 40% paper, and probably the balance might be some rigids. It's a more modern plant, as you can see, and we're getting the paper away from the flexibles is the big deal. It's really hard to do that. And then once we have that paper separated, we're separating the types of flexibles into LDPE and PP, using our additive then to control the melt flow rate so that we can make a bag from that, a waste bag from that. And the bag is obviously a blow molding, an EBM process, and I mean, it's very important for most processes that you get the flow rate right, but if you can imagine if you're blow molding something like bubblegum and then it just bursts because it's got the wrong flow rate, the machines just get destroyed. So you don't get too many chances to supply somebody if you haven't got the exact melt flow rate needed for their machine. So, and here's just an example of our material being blown into bags and wrapped into a bag that you might buy in Aldi or Tesco. And so that's kind of a big breakthrough that we were able to make because we had the melt flow rate additive that allowed us to make that kind of bag. So there's the bag there, and you can see the quality of it. It will still have gels in it because when you're using any recycled material, you're going to get some gels, and that's probably something we have to try and get over in the recycling industry, especially waste bags having a few gels in our book is not a big deal. But for some marketing people it is, so we have to try and push on and try and get the consumer to accept that waste bags might have some specs in it, but it's fine. But that's a 12 micron bag, so that's probably the thinnest bag you can find. It's not like a big agricultural film bag. So we're able to blow that. You can easily then blow anything thicker than that. And then finally, to move on to the Innovate UK part. So having success and some experience with the bags and with flexible material in Glasgow, we're now opening up this 25,000 tonne film recycled plant in Durham. And it's kind of, I suppose, when we started in Newcastle, it was 10,000 square feet, and then we went to 27,000 square feet in Glasgow, and now this is 70,000 square feet. So it's by far and away our biggest project. It'll handle 25,000 tonnes of film per year. The collections are coming from Suez Flex Collect, where they're doing house-to-house collections of flexible material. It's coming from back of store, from front of store, but the back of store, not the 98.2 stuff, but the really bad stuff that they can't get rid of anywhere else. That's what I mean by back of stores like Tesco and Sainsbury's. They gather all their packaging and they can get really good quality 98.2 material, which they get good money for. But then there's all the other stuff that they can't get any money for and they pay a gate fee to get rid of. So we'd be taking that. Or the front of store, which some of you have seen, Tesco and Sainsbury's have started collecting material at the front of the store. We would take that in as well. So we take it in baled, we shred it, we wash it. We do everything that I said we do. The difference being that instead of black material for film, the material that's problematic here is multi-layer material. And that is about 30% again of the waste that comes in. But luckily, the multi-layer has a different density to the monolayer. So that multi-layer is when we put it into we shred it, wash it, put it into the Boss machine, that multi-layer will get flushed down as a heavier density material and separated from the monolayer. The monolayer would be the bit that gets caught in the top in the whirlpools. And then once we've separated that, we can recycle the 70% monolayer into a bag, or into LDP is often used to add to some rigid products as well, but it'll be a combination of the two. I don't know how much time I have, I don't want to take it in.
Are you nearly done now?
Yeah, we're a couple of minutes? Yeah. So, I just play on here just to show you the waste that we're taking in and what type it is for this facility. So they're the types of collections we're doing: curbside, front of store, back of store, and then just MRF collections. So that would be after it goes through MRF rejects, I think they're probably called, which is the film fraction from any MRF. But there's unfortunately plenty of feedstock for us because we can take in post-consumer very highly contaminated film, and there's a lot of that on the market. And I think the next bit here of the video will show you just what it takes.
Second UK facility in.
So I'll turn off the sound. So that's typically what it looks like when it comes into us baled. So you can see it just looks like the heap that we had of rigids, except the flexible equivalent. And then we'll be producing a bag from that. Or as I said, we produced an LDPE product, a pellet, and then that pellet will be supplied to people who make bags. So we don't make any of those products ourselves. We supply pellets to people who make all those products that we've showed so far. So that's it. Thank you.
Our last speaker is Tom from Mcdonald. Cool, yeah, so I'm Tom McDonald. I'm a reader in sustainable materials at the University of Manchester. My talk's going to be a bit more technical. It's about, but it's been fantastic actually hearing and being able to follow on from
some of the talks earlier. So the project I'm going to be talking about is smart recycling, and it's about a data-driven optimization of understanding quality of post-consumer HDPE, and it was funded by the Smart Sustainable Plastic Packaging funding. So I'm not going to spend long on this slide because I think actually the talks before have really just primed and given an overview of the process. I think the key thing I want to say is in terms of HDPE, it's one of our most widely used bottle plastics, just under 50%. We collect quite a lot of it, but the key issue, again, when we get round, and we heard a little bit about that in the previous talk, is that actually PCR is this post-consumer recyclate material is a very variable product. And really, it's a variable product because, of course, you've got a range of different plastics, a range of different grades of high-density polyethylene are used here in your bottle, and also you can have contamination with other plastics and also with product, and you can also get degradation in the process. So a lot of plastics, again, go to the lower value applications, but as we heard, of course, what we really want to do is go in a more circular manner. And really, to address this, we need to think about what is this knowledge gap that allows us to understand the properties of our PCR and how lightly that plastic is going to perform in bottles. Because really there's two aspects to think about from the side of production. If you are a recycler, you want to maximize the quality of recycled plastic, but also if you are putting the plastic in your packaging, you need to be able to select that material efficiently. So I will skip this one really because, again, I think we've heard most of the key points here. But I guess the key thing is we have polypropylene is a very common part, a common contaminant in a HDPE waste stream. And that's because typically the caps of bottles are going to be polypropylene. The bottle itself is going to be HDPE. They have the same density, so in float sink tanks, which is one of the main ways of separating them, they end up in the same stream. And I'll come back to that because that is a really key aspect. The other thing, of course, is these materials are sourced from very variable feedstocks themselves. And here we can see an example of broken bale where, again, there's many different types of plastic in there. So what did we do in our project? So our key question was how to understand how differences in PCR influence the performance of plastic in an application space. So what we've done is we took 28 commercial grade PCR materials and we put them through essentially the biggest selection of techniques we can think of that have been shown to be really informative. Many of them ones that could be commonly used in labs in recycling plants, but also ones that are much more specialized like solid state NMR or rheology, which might not be a common technique that's available in all labs for plastics reprocessing. And essentially what happens if you take a lot of samples and do a lot of tests, you're going to generate a lot of data. So here's just an example of a type of thermal analysis. And you don't need to worry particularly about what this data shows, but the key thing I want to emphasize is in any data there's many different, what I'm going to call features. So a feature is something that can differentiate the material. It can tell us something about that material. And so actually you can normally, when you do analysis, you might look at a few simple features, like in this case, this is the melt of the polyethylene, and this is the melt of some polypropylene contaminant. You might look at things like the temperature it occurs, how much energy is associated with that. But actually, there's more data in here than we'd normally look at. So what we wanted to do is use a data science-based approach, rather than just looking at single features, where can we extract more value to really understand the samples. So out of our data set, we generated about 3,300 different features. And this was a lot of work led by Andy and Peijs. So the other key thing we wanted to think about is across, say, a pack's not lifespan, but a pack's journey. So if we think about it, when we have the production of a plastic, we've got the actual chemistry of the backbone, we've got the architecture of the polymer. When it's then processed, we need to understand its melt properties. Its crystallinity is really key in driving a lot of its actual behavior as a solid. We need to understand how processable it is. Then we need to relate to the mechanical properties and bottle properties. So actually our study is the largest study, well, we wrote it in the paper and no one disagreed with it. So it's the largest study of real world PCRs to date. And so by essentially looking across all these different aspects, we're really able to understand the material and link to its properties. So what does that look like? And I'm trying to represent that in a single figure here. Here's our different samples that have been fed in. And in this case, we've done a range of different analysis techniques. I'm not going to talk through them all, but there's some are thermal tests, some are rheology, looking at colour. And essentially, this middle part shows all those different features. So all the different aspects of the samples that can differentiate them. And at the bottom is our different types of samples. And again, on this axis will be different features within, say, infrared analysis. And so we can see that some samples show much stronger signals in certain places than others. So again, we can use that to differentiate them. But really, it's like, how do we take all that data and make it accessible? So we use a data science tool known as principal component analysis that allows you to take all those features and say, what if we combine them? Which ones are the most informative? And we do that for every technique. And then we then do another analysis that clusters those. So this is our really key output I'm going to talk through in a minute, which actually allows us to look at quality of recycled plastics. So here we can see on that right, that clustering analysis. And essentially what we've done is, by looking at all the different features in the material, we can identify which features allow the material to be separated. So in this bottom area here, we've got our virgin samples labelled with B's, and then we've got other PCR samples that are very similar to these. So essentially, if you were trying to produce a high quality PCR, you'd be looking to have it in this section. And if you were trying to select a PCR to put into packaging, these materials would probably be the quickest to substitute in for virgin plastics. The samples over here have a lot more polypropylene contamination, which is one of the main differentiators we saw across all PCR materials. And this section up here is a bit more diverse, so we see changes in rheology, some mechanical properties in this space. And so this is a really key aspect that we view as a selection tool that allows you to screen materials. So one thing I showed is we had this sample set and many different testing methods. And one of the things we recognized that it isn't going to be possible for most people to do 6 different testing methods, including things like rheology testing. Those aren't necessary techniques that are available for everyone. So we wanted to think, can we reduce our tests down? And so what we've done, and again, what we've done is essentially looked at our different testing methods and said, what if we just choose 3? So here's different combinations of 3 tests. And essentially, we look at our data set and say, if we use these 3 tests, how much do the data points move? So how much information do we lose? And really, so if we've got a blue color, we lose the smallest amount of information. And if we have a yellow color here, we've lost a lot of information. So the data points have moved a lot. So we're not really able to, if we've got a yellow color, we're not really able to use those combinations of tests very effectively. But the great thing is, these 3 tests, FTIR, thermogravimetric analysis, and mechanical tests, are quite widely used in most plastics recycling companies, and they're quite available tests generally. So actually, we found that these combinations of tests, these 3 tests allow us to attain about 80% of the same data as all 6. So really powerful selection. So that's a key thing, and again, that's something we're working on developing forward. The other key thing we've shown, and this is very widely known, but again, when you read papers and look into the scientific literature on this, it isn't often robustly shown in a large data set, but we've shown that polypropylene content, so our bottom axis is polypropylene content, so more polypropylene, less polypropylene, and on this axis is strain at break. And essentially what you can see here is our virgin samples, which have no polypropylene, have a very high strain at break, and as soon as you have polypropylene contamination, you drop off mechanical properties dramatically. And this is, again, some of the things we've heard about in previous talks about the importance of being able to separate your polyolefins really allows you to generate a product with much higher value. So I'll pull together a few key things here. So we've shown that PCRs can be effectively identified and classified with fast and easy testing methods. We did a test on 23 different HDP resins in our paper that's published here. And we showed how you can extract different features and allow you to differentiate the different materials. We can allow to select materials that compare favourably to virgin HDPEs with 3 simple tests. And we've also looked at some relationships that we've identified as well. We're currently also working on identifying other properties, and there's a few other things I wanted to mention, just that we're also working on. So we've looked at an economic and environmental analysis of practice and policy changes. So we have some papers that will be coming out in the next 3 or 4 months on this topic. This isn't one I led, but experts in supply chain have led this. We're working with one of our project partners, we're working with Unilever to develop a data science tool so that they can embed it within their organisation and use it to select materials. This is also something we want to be releasing more widely in the next year to the wider community. We've looked at processing and additive selection to improve some of the properties of HDPE. I don't have anything I can share at this stage on that topic. And we've also got a study that we will be publishing on linking the data points here. So when we take samples from our clustering analysis and do bottle testing, which bottles perform best. So really to take it through and be able to understand how to relate these parameters to bottle properties. There's 2 things I want to quickly just talk about at the end. Is a lot of this work's been really critically enabled by the Henry Royce Institute, and one of the research areas within the Henry Royce Institute is chemical materials design. It's also one I'm a research area lead for. So this is an area that is about pioneering methods in computer-aided design, machine learning, and robotics. So you saw in our work we used AI, or not AI, but we used data science tools to really accelerate the work we were generating. This area is also about accelerating innovation in the discovery of new materials with low environmental impact, and also developing faster, more sustainable solutions. So the key thing we used a lot of is in the Henry Royce Institute of Manchester. We have the Sustainable Materials Innovation Hub, and this has a wide range of different characterization equipment, processing equipment, so we can look at weathering, barrier properties, processing, thermal analysis. Essentially, a lot of the techniques I talked about are available in the Henry Royce. The Henry Royce is available to everyone, so it's the UK's National Advanced Materials Institute, and so if you're a company, an SME, there's many different schemes to interact with us that can essentially help you accelerate and innovate in your research. And in academia, we're really passionate to help you solve some of the problems. So if you do have any things that might be of interest, come have a chat to me later. So I'll finish there. Thank you for your time.
Thanks, Tom. This leaves us with maybe 5, maybe 10 minutes for still some questions or for our speakers. But I would like to maybe start off with a question is, polymer recycling, I would think, would be one of the best business opportunities you could get into, because there's a very big push towards recycled content and circularity, and this is now really what everybody's after. But then if you talk to the industry, they're all struggling or actually going bust. And I'm a polymer scientist, I don't know much about economics, so can some of our speakers or maybe from the audience explain to me why this is? Why is the plastic recycling industry really in such a poor state, also in terms of opportunities, and whereas from, let's say, the trend, you would think that there would be massive opportunities.
Yeah, I can give some first-hand knowledge with that, unfortunately. So I think 2 things. I think one is you could be in the position that we were in, where you can't sell your product because you can't get the melt flow rate properly. You can't get it to a proper flow rate for buyers, and therefore you're selling it for low-end products, and therefore you're only getting 300 or 400 quid a ton for your product, and it's costing you 500 to make it, so that doesn't make good business. And then I think secondly, polymer prices in the last 4 years of virgin material have just collapsed. So people are buying virgin in for £400 or £500 a ton. So again, if you want to then charge them 600 or 700 for your recycling, because that's where you got to make profit, they don't want to buy it. And a classic example at the moment is the PET market, where you know, it's much more established, it's the oldest market, but you can buy PET in at the moment for, I don't buy it every week, but in the last 6 months you could buy it for 600-700 quid a ton, virgin from China.
And then they put a recycled plastic sticker on it.
1,200, so you know, people just made a choice of saying, we're just going to buy virgin, and they just switched. So brands that were using PET for bottles just said, well, we'll have a more profitable year this year. We don't really have to do it by law yet, so we just pay the tax. So the tax is, I think, 100 quid a ton or 200 quid a ton or whatever it is, and buy the virgin in for 600. That still is 800, and recycled price is 1,200, so we're still quids in. So that's just a fact. So I mean, it's not this wonderful opportunity. I would say everybody in the recycling industry is just on their knees because of virgin prices, and also because I think, well, in PET they've got the quality up to where they need it, so they're getting good prices, but they've been undercut by virgin prices. But I think in the polyolefin market, they can't solve the amount of flow problem. And I'm not saying that because we've solved it, but I just know because we were in that place ourselves.
But that's the price. But there's also a drive towards recycled content. So then, you know, no matter what the price, there has to be recycled material in there. But I also see, is there a problem with like traceability, because people may sell you some material with 30% recycled content, but how are you going to check? Is there any, you know, history on this material, or you just take them for granted? Is that a problem?
Accreditation companies that do that, and they have audits, and so there is, you know, but they're independent companies. So I mean, I think it's difficult to come. You know, I think the market is in its infancy, and it's, I wouldn't say it's the Wild West, but it's in its infancy. So everything is just starting to get established. So there are lots of kind of gaps, if I'd say, and so it's not perfect at the moment. But I think the biggest thing is that, I think the biggest change really to address what you're talking about would be the packaging and packaging waste regulations, the PPWR. And that is a big change. Up to now, you had to pay a plastic tax if you didn't use 30% recycled content. But with the PPWR, you won't be allowed to place your product on the market if you don't have 30% recycled content. So you can't say, well, pay the tax and switch to virgin. You actually can't put it on the market, and that comes in 2030, which is sooner than we probably think in terms of we've got to change all your systems in the plant. So I think that regulation will change, and I think then what you're talking about, the bonanza maybe for recyclers might start then, because people will have to use it. And then it will come back to your question of how do we know?
Yeah, well, I also heard rumors that people are selling virgin material as recycled material, and then, yeah.
Something we've been talking about like, well, there's a big concern. You haven't got any checks in place, and you just say anyone can label anything.
Exactly.
And it undercuts the manufacturers.
Okay, are there any questions from the audience? That's ladies first.
I've read explanations. I want to ask actually David and Thomas after two things. One, what happens when you can't sell the recycled product, and well, yeah, what happens then? Because I've heard stories as well from other companies that they have to sell it to other distributors, and then they have different ways of distributing, let's say, and sometimes just end up in the ground.
Yeah.
Sadly for both sides.
I'll give you this. Sorry.
Oh, sorry. And this is for you, I think mainly David. And then for Thomas, I kind of disagree what you say about the virgin and the PCR graph you showed with the strain, because it depends what the end product is. So it could be good if it's stiffer, for example, than less stiff, because the virgin should be less stiff, I assume. So, yeah. But yeah, what happens when the product is not sold?
We can't sell it. I suppose that's why recyclers go bust. So back to your point, and we were just storing it in a warehouse for 2 years until we could, trial our materials using the flow and additive, and then that allowed us to sell it. But It's really difficult. It has to, like the size of the plastic lumber market in the UK is about 12 or 15,000 tons. So if you've all of the recyclers heading to that market, it drives down the price, and it's just not an offtake that is sustainable. So I think that is, you know, a reason that a lot of plastic recyclers go bust is the sales. They can't get the sales to support their business.
But do you think that's because of government regulations, or because that's the way it is? Because you say like they sell from £600 from China and you sell it for 1,200 because, well, you have to the PET, for example, which is unfair, right?
Yeah, I think there's, I think there's two sides to the story, because, you know, brands can't buy it because it doesn't work in their machines because it's not the right fluoride. So that's on that side. They're looking for a product that will make it. Like I got a cold call somebody yesterday, emailed somebody yesterday and said, you know, we can send you this, and they're making bins, and he said, look, you can't, because we need a melt fluoride of 5, and no recycled product has ever been able to give us what we need, except for we chop up bins, shred them ourselves, put them back in, and then we've got the right flow rate. And so I've just got to go back to them now and say, actually, it's different. We have this additive, we can now supply you, it's new, etc. But up to now, they would have tried, and to be fair to them, you know, they've had a lot of product that arrives at their door saying this will work, from hopeful recyclers who don't know they even have the problem of melt flow rate because they've been just focused on purity. And so then after a while, they're just like, oh, another recycler with purity, like, you know, give me another one of these. So, like, it's difficult. And you know, my biggest point here today would be, it's not talked about. It's like, I don't know, it's like, I could give you a lot of examples of problems in society, but I haven't heard one conference ever somebody saying, let's talk about melt flow rate. Ever. Just, I don't get it.
Maybe move on to the next.
Yeah, thank you. My question is related to the topic that we mentioned about the state of the industry, and you picked up an example on the PET. I think, and my question is related to the economics of the recycling. So for every business to operate profitably, there is a cost and then there is a profit on top of it. The challenge, probably what I see in the recycling plastic industry, is this volatility, which goes from the recycled plastic can go from £1,000 to £2,000. Do you think there is a kind of a, what you said, consumer switching or your customer switching? There's a mistrust, and there is something needs to be done to be more transparent about what the recycling PET would cost for your customers.
Yeah, I mean, I don't know the PET market that well because we're not in it. We're in PPE and LPE. We don't take in any PET because that's well serviced. The industry is well established. It recycles very well. It doesn't need us. I'm just hearing that back from other PET people. I'm not directly involved, so it's hard for me to answer that directly. But I know that people have made the switch, and PET sellers or recyclers are finding it very hard to sell their product this last 18 months.
And I think the switch, and I'm sorry, maybe you are not directly linked with the PET part, and maybe in your part. I think it's from a consumer market perspective, the consumers look for a stable pricing. But what's the challenge on the recycled plastics industry is the volatility, and it goes up to wildly with 2x. And it's probably the only recycling industry where the recycled price is much higher than a virgin material price. So how do you engage with the wider society to accept that fact? Or is there a need to be more transparent and put forward what's the real cost of recycling?
Yeah, sorry, I understand, sorry. I think that applies to any polymer, and I think really what we found is that where we have proved that we can supply a product, so if we're making the silicone cartridge, or if we're making a bottle or whatever, and if we then get to the standard that is needed, they don't have any problem paying us for the material. So obviously it can't be thousands extra, but it's like they don't have any problem paying a small premium, or 20 or 30% premium on version for that. So I don't think if you achieve the standard, the price isn't really the issue. I don't know what you think in Barry. If you're
Yeah, absolutely. So the way that I would approach it, because I deal with a lot of brands and retailers direct that want to purchase our material, is explain to them that actually to do the right thing by including recycled content, lowering your carbon footprint, is going to cost you more, and here's why you should do that. And it is, for example, if you're a brand and you want to put products into a retailer that has a target of, I want to see 30% recycled content in my product by 2025, I sell that to the customer by saying, if you do not do this, you will be out of line with that retailer's objective. Therefore, highlighting it to the brand, and they go, maybe an on-cost of 3 to 5, 10% max is going to be better than no business with that retailer as I get robbed. Also, I don't want to get too much onto the anti-plastic sentiment because I know we're running over time, but that's also a massive, massive challenge there. So it's a case of realising that the value of recycled material and the sustainability benefits is more than simply it's going to cost me more. If we don't address it collectively all together, it's going to cost us all a hell of a lot more without it. So yeah, it's beyond simply the pricing is the sales tool really. Thank you.
All right. I think unless it's very short question, which also can have a very short answer.
Yeah, Jack. Thank you very much for your presentation. This question really goes to David and well, what you do. You don't 100% recycle all of these. What kind of waste do you guys produce?
Yeah, so we take in around about 50,000 tonnes of polypropylene on an annual basis, basically a rule of thirds. So a third of that is non-target material for our food grade FDA materials, so that goes into paint can recycling, kind of what we call the jazz stream. A third of the material is our target material for content of application, and a third of the other side of it, sadly, is either non-target polymer that makes its way into our facility. So that's fibre, that's PET, HDPE, because we are only as good as our suppliers are able to give us here. So the upchain people that supply us, sadly, the contamination there of non-target is a lot of what's happening there. Any flexible material, any things like broken glass, aluminium cans, stuff like that, we end up having to send out of our facility. We have plans in place, perhaps maybe with someone like Impact, to be able to make sure that that collective HDPE, PET, and LDPE flexibles can be recycled. But yeah, sadly, we are only as good as our suppliers give us here. So I would say 20% of what we receive in, we can't really do much with. Best case scenario is we bail it, send it to somebody else for specialist recycling. But sadly, some of it, especially organic waste, because people don't always wash up their pots and things when they recycle it, that has no further value really, sadly. So that ends up having to be specialist recovery, energy for waste, that sort of thing. So yeah, around about 20% sadly is what we can't do. But if our suppliers start doing better, then we will have higher yields. It's all about the quality of feedstock. I imagine you'd say the same thing.
Yeah, so we take in general waste, so it's not pre-sorted at all. I'd say 60% is PP and PE, so that is the flowing fraction that we looked at that we're making products from. 40% would sink, and so that 40% would be split between polystyrenes, which are kind of under density of 107, and then all the other plastics that are above 107, PVC, and PET, all these other plastics. So we get very little PET in because people have picked it off because it's valuable. So I would say 60% is the polyolefin, that gets recycled. Of the 40% that's left, we separate that into polystyrene, HIPS and ABS basically, and non-polystyrene, so that's half of that. So 60 plus 20 is 80 getting recycled on the rigid line. And then the other 20 is like yourself going to incineration, or it's just mixed plastic, so it can't be sorted anymore.
Specialist recovery as opposed to.
All right. It was a slightly longer answer that question that I had hoped for, but I think before I let you go, I'll take the opportunity to just bring about one thing, which is around a bid for EPSRC, which the University of Manchester, including Tom and Warwick and UCL, are at the moment putting together. So we're leading a bid which is invited by EPSRC to go to the next round for creating one of the new manufacturing hubs, sustainable manufacturing hubs. And those are big bids. This will involve something like 10 million pounds of research funding for 7 years, which is going to fund 60 to 70 postdoctoral research years over these next 7 years. So there's a very big opportunity, but we would like to avoid that all this money then, if funded, doesn't end up doing academics doing sort of their own hobby. So we really want to co-create this program together with industry so that we make this program work for you as an industry. So if you think that there is an interest to be a partner in that program, please grab me or Tom or go to the WMG stand. There will be a flyer that gives a little bit more info because at the moment we're really in the stage of creating the final proposal, and if we can get some input from you guys and how you want to be involved, that would be very much appreciated. That's all. Thank you.
That's really interesting. I'm not interested in what you just talked about. My name's John.
I'd like to just start by introducing myself. I'm Andrew Dove. I'm a professor of sustainable polymer chemistry at the University of Birmingham. And I just thank Sally for the opportunity to chair this session. I think it's going to be a really interesting session on depolymerisation and chemical recycling. It's an area that I'm personally very interested in with the research that we're doing to develop new types of chemical recycling. But if any of you have come across this document, the Sustainable Plastics Policy Commission that the university put out earlier this year, which I'll happily talk to any of you about if you're interested. We actually find some of the key findings were around the opportunities for chemical recycling in terms of scaling up to close the current gaps in the recycling infrastructure, but also potentially helping with complex plastic waste and provision of higher quality feedstocks for the recycling industry. We've got 4 really great speakers that I'm excited to hear. Brooke Wain from the University of Portsmouth, James Cosby from Longworth, Charlie Breese from Sylatech, and Bushra, who is apparently from Stopford, but I thought you were from the University of Birmingham, Bushra. We can talk about that at lunchtime. We can talk about that at lunchtime.
I did actually tell them.
So, from both Stopford and the University of Birmingham.
University of Birmingham.
We've got some really great talks, some really great tech to hear about. You don't want to hear me rattle on about it, so I will pass over to our first speaker, who is Brooke, who's here. Thank you.
Thank you, Andrew, for the introduction. So I've travelled up from Portsmouth, so from down south, and I'm Brooke. I'm representing the university, the Centre for Enzyme Innovation, and also our new hub. So we're now the P3EB hub, so preventing plastic pollution via engineering biology. I just want to share with you a couple of, share you some information on quite a new novel technology, which is kind of coming through in the pipeline. So in a nutshell, we're trying to use enzymes now to break down plastic, polyesters and particularly PET. And at the centre, we take a lot of our inspiration from nature. Everything we do comes from nature. And if you look at this image, most people are drawn to the green, but what's equally of importance is that in the brown. So that's the decomposition, that's where things are breaking down. Now, if we look closely at that leaf, you look at the waxy cuticle, the bit that gives it the waterproof properties and that shiny gloss. That substrate is natural and it's called keton. And although the structure is quite complicated, what's shared is a bond called an ester bond. And that's the repeating unit which goes through. And this is a bond that's hydrolyzable by a lot of enzymes, which are released by microbes to break it down. Now, those enzymes and the family which works on these keton are ketonases. So scientists like to name their enzymes by what they break down, so the substrate, and then just add A's on. So protein, proteases, keton, ketonases. Now, if you look at the substrate PET, so that's a synthetic polymer, you can see that although the structure is different, that repeating unit, that bond, that ester bond, is shared and can serve between both. So the idea is that if these enzymes can break down that natural substrate, can they also break down the synthetic one? Which they can. So if you do want to speak to me more about kind of the history behind enzymes, what they are, where they come from, I could talk for hours about it. So I have a poster over the poster kind of section. Come find me and speak to you about it because it could take a whole lecture in itself. But what's important is that enzymes are like small scissors. They cut the bonds up, they separate the polymer chains, long polymers down into the fundamental building blocks, which is obviously of importance for us because you break down PET, you get the raw virgin kind of monomers back out. In the lab, we do reverse engineering of these enzymes. So think of an enzyme as a machine. Take it back a step, you get the parts to the machine. So you assemble those parts by following kind of a recipe or a journal or a manual. So we reverse engineer that back. You can choose a part from an enzyme that you want to change. You choose a protein sequence that you want to mutate and go back into DNA sequence. Really interesting stuff. So if you are interested, please come and speak to me afterwards. But we do a lot of optimization because those enzymes in nature, they do work, but they are slow. So for any industrial process or for commercial viability, we do need to improve them. I'm showing you this just so you can visually see that it does work. So we're focusing mainly on PET and polyesters, but what you're seeing is a piece of PET film which has been treated with an enzyme, and over time you can not only see it degrade, but it disappears. It hasn't actually disappeared, the monomers are still there, but they're in solution, which is colourless, but the plastic itself is no longer there. Now, this idea, obviously, why is this relevant, why is it important? We all know about kind of current recycling processes. The majority of them are on that linear pathway, and we're all trying to move towards circularity, which is why we're here today. And that's one of the key highlights of the enzymatic route, the biorecycling, is because once the plastic product has been broken down, those monomers, so for PET, for example, you have terephthalic acid and ethylene glycol, those monomers can then be extracted back out. You can purify them, which can either be fed down into downstream processes or used to repolymerize the same strength plastic product with virgin-like qualities. This led to the centre that I work in, so the CEI. So this was kind of established about 5 years ago. And without going into detail on every single team here, what you have in Portsmouth is a facility where you can bounce between different teams and different labs. So you have the team who do all the bioinformatics, they discover new enzymes, you then move over, they hand over those enzymes directly to the team across the hall, to the engineering team who will mutate them, optimize them to make them more durable, more thermostable. This then gets kind of shoved down to the end, which actually, although there are 3 teams, they're more like 1. So you can deploy these enzymes, but obviously when you're deploying them, you're working alongside industry to find the best process. You're working alongside the apply team who are trying to, once they treat the plastic, get the monomers out in the best and most efficient way. And obviously alongside that is how do you actually make that a system and process which can be established into a commercial company. So not only is this kind of research and academic side, it is now coming through into industry. So there's a company in France called Carbios who are now opening their first pilot plant next year. So the French government have gave some of their waste to an enzymatic team and then some to a chemical team, but they're going to be taking 30% of the kind of France's waste, PET, and turning that into monomers, which are of use. So it's not just an idea now, it is being pushed through into industry. But that comes with challenges. Scaling up from, this is my lab, so the bioreactors I use daily, taking the bioreactors, which is already a scale up from 1 mil Eppendorf tubes in a lab up to kind of a litre, but then taking a litre up to a massive 1,000-ton plant, it's a big difference. So there has been techno-economic analysis done in 2021, and without going into too much detail, what's important from this tornado plot is that on the right-hand side, you're seeing the variables which need to be optimized in order for this to be a viable technology. Things like the depolymerisation extent, obviously you want an enzyme to be able to break down 100% of plastic rather than 80%. So you're seeing the mean rate change in the price. Not only was the TA done, but you also had the LCA, so you had the life cycle assessment done as well. Now this not only highlighted and supported the areas which need improvement and optimization, just for our research teams to focus on, but it also highlighted a process. It was the first time they actually published a statement of this is an idea of the system of what they use in a plant. And if we look at this, I know it's quite overwhelming, but the information that's key is if you look at the blue section where you have the enzymatic depolymerisation, that's working. That's the enzymes you work on, that's the ones you've optimized, and we do have now enzymes. Nothing's perfect, there's always room for improvement, but we have got enzymes which are now working at a high efficient rate. We look at the red section, the repolymerization, that's plastic synthesis, as we can all agree. That's already quite efficient, so we don't need to optimize that area. But the 2 areas which need improvement, majority, is the yellow, which is the feedstock. I'll go into why that's important in a second. And then this kind of greeny section. That, at the moment, has chemicals we use, such as sulfuric acid, sodium hydroxide, as a byproduct of sodium sulfate. So that's not ideal. Now, this has actually been optimized, but I can't share that yet at the moment, but this is in the works. So taking it back to the yellow, why is that a problem for us? It's the crystallinity. So the enzymes we have at the moment, they like areas which are amorphous, not crystalline. What is that? It's where the polymer chains are either aligned and structured or they're exposed. So in a crystalline area, the polymer chains are all hidden, the bonds are hidden, so our enzymes can't attack that. But when it's amorphous, it's when the bonds are more accessible. So to see that visibly, you've got a piece of untreated film, and you've got a piece which has been treated with an enzyme. And you can see that the enzyme works away around the amorphous bit, into the amorphous bit and leaves behind the crystalline regions. This means that if you have a plastic product with high crystallinity, our enzymes don't like that, which means we have to do feedstock treatment, washing, have to amorphize the plastic feedstock, which adds costs and greenhouse emissions. If we can have plastic products which are designed to be less crystalline, fantastic, or we need to find enzymes which can target the crystalline. So it's going to be a synergistic approach to either the polymer design or the enzyme optimization. I was going to talk to you a little bit about bioreactors, but I think that might be a bit too kind of scientific for this talk. But in a nutshell, as I said, one of the byproducts of the PET hydrolysis is TPA, it's that acid. And because it's an acid, we can add a base to track the degradation quite nicely. So bioreactors are completely autonomous, so it means we get a complete comparison and we get the data, large data sets of temperature, pH, monitorization, we can add whatever we want in them. We also use the bioreactors for fermentations because you need obviously a lot of enzyme to break down a lot of plastic. So how do you produce that on a large scale? We can use expression systems such as yeast, which are already known to produce insulin, or as I said, from Burger King, they produce a kind of soy protein that's already well established. So the idea of not being able to produce a protein isn't a problem because there's already well established systems out there. So taking it back to that tornado plot, one of the bits I mentioned earlier, the highlight, is that monomer recovery, so the ethylene glycol and the TPA. TPA is really valuable, really expensive and really useful, but obviously it's worthwhile as a byproduct for getting all the monomers back out. So after hydrolysis, we're left with what we call a monomer soup. Although in here, this is a bioreactor, although it is showing it cloudy, that's just where we have such a high concentration of TPA being produced, it's just crashing out naturally. If you change the amount of plastic in the solution, that would be clear at the end. But what it's highlighting is that with TPA aspect first, we can drop the pH, we can acidify it, we can do various chemical processing to get the TPA directly out, and same with ethylene glycol. So at the moment, we're using distillation, which takes advantage of different points, boiling points, melting points, and that allows us to get pure monomers. Now, the reason why I'm mentioning this for circularity is that we've done loads of other characterization on these monomers, and what you're seeing is that the quality and the purity is that of equal or more pure than the original monomers, the original feedstock, which went in to make the plastic product to start with. It is important to note that this here is done firstly on, as a science field, on perfect kind of amorphous film. This isn't post-consumer waste yet, but it is being done. I haven't got the data here to show you as beautifully as this right now. So what about the other polymers? Everything I've spoken about at the moment and everything that CI has been doing a lot of work on has been done on polyester, so on PET. But obviously there's not just PET that's the problem. There's various other polymers which we can now target. Things such as polyethylene, that's a carbon-carbon hydrogen backbone, that's really hard to break down at the moment. We are doing research on that using yeast enzymes, but that's really hard to break down at the moment. But things like this, so polycarbonate, polyamides, although some have the carbon-oxygen bonds, some have the carbon-nitrogen, we are now targeting this. How are we targeting that? That's where the new hub comes in. So originally we were the CI, we're now the P3B hub. And this is amazing. This is where we have suddenly brought together the majority of all the universities in the UK who are doing an area focused on some plastic degradation from polymer designs. It's not just the enzymes anymore, it's everything. It's the enzymes, it's the monomers, the byproduct at the end, it's the process, it's the policy, we're looking at polymer design. So rather than having different teams working kind of on their own, we're now bringing everyone together. It's led by the University of Portsmouth as the hub centre site. However, it's all these big names, I hope you know, because these are some fantastic scientists, all working not only with us, but now also with industry too. So we have large industry partners, this is not all of them, who not only provide information and knowledge transference, it's also that idea of guidance. So it's now working together alongside academia with industry. So there's 8 packages, that's how it's going to be achieved. I'm not going to go through every single work package, talk to me after if you are interested. But the ones I want to highlight, so the ones in grey, so there's 4 work packages still being focused on the enzymes. So the enzyme optimization, the discovery, the deployment of them, how we can change the polymers to make the enzymes break it down faster and further. So the enzyme discovery part is still important, but we're now obviously branching forward. So where it's highest in bold, we're also now looking at standards, looking at policy, and public engagement, outreach, getting trust out there, and spreading the word. So it's not just the science anymore. So the message I'd like to leave you today is obviously biorecycling. I'm biased, I love it, I have complete faith in it. However, it's not the be-all and end-all. It's not going to be the one recycling technology which is going to kind of pioneer everything. It's going to be working synergistically with everything already. So every plastic product has its most preferred way of being recycled, whether that's mechanical, whether it's chemical. So it's not going to be biorecycling, that's it. It's going to have to be everything, not just biorecycling, but for chemical recycling too. Everyone needs to work together, especially when it's to do with the polymer chain breaking down. Mechanical recycling, as mentioned, I don't know if you guys were in the lecture theatre one, mechanical recycling is quite efficient now, and it has lower reduced carbon emissions. That's when the polymer chain doesn't need to be broken down. If the polymer chain does need to be broken down, so you actually extract the raw monomers back out, that's where the enzymatic and biorecycling will fit in. And that is everything in a quick whistle. So thank you very much for listening.
Thank you, Brooke. Really interesting talk. I'll hand straight over to James.
Thank you. Hello everyone, nice to see some friendly faces and some new faces. My name's James Cosby and I am the R&D manager or innovation manager at a SME called B&M Longworth. I'll give you a little bit of an introduction to something called DECOM, our patented technology. We'll talk about pressolysis and degradation through pressure, and we'll give some examples of how this works and how our process works. So we're an interesting company. We act like a startup sometimes, but we've actually been around since 1976, led by kind of our visionary chairman, John Norris, if any of you know him. And we started off as a cleaning company, right? So we're cleaning polymer filters and metal components. And through this, in the early 2000s, we managed to develop a technology that would actually reduce and eliminate the use of solvents. Now this proved so well at depolymerizing things that we actually turned it to composites. And from there, as some of you may know in some of your research institutions, this is growing and growing. Moreover, we're now seeing scope to use this technology for polymers and polymer recovery. So, if any of you do have any CapEx, let us know. So, pressolysis. It's a zero-emission reclamation technology. We only require water and energy. We use superheated steam to fill our vessel to high pressures and decompress it. This is a bit like steam explosion, perhaps if any of you have seen that, but it's repeated, so we decompress. Those rapid pressure changes enable a mechanical fracturing. As well as that, it removes volatile components from the surface, enabling a speedier and more efficient depolymerization, especially for thick materials, and I'll show you some examples of that in a minute. But that mix of chemical and mechanical really allows DECOM to work with such a wide variety of materials, either to melt, to hydrolyze, or to depolymerize in other ways. And this is just a unit here. So, because we're using superheated steam and the process is patented, we can operate in a wide variety of space in terms of temperatures, pressures, and pressurization cycles. For example, we can debond and use superheated steam to penetrate a multi-layered material and debond an adhesive. Or we could simply melt away a different polymer. In some of our units, what we can do is we can separate various polymer materials by melting one and keeping another. And primarily, lots of our work has been in composites, and that's where we've been doing depolymerization, both of thermosets and thermoplastics. And this, because we're at different ranges of temperature and pressure in superheated steam, we can kind of change our levers to either go for a hydrolytic mechanism, that's predominantly, as you've seen here, for hydrolytically sensitive materials, so your polyesters, your polyamides, your polycarbonates,
But perhaps you have a thermoset like an epoxy which has no hydrolytically sensitive bonds available. And in that case, you could go through a thermolytic process, which works a bit like pyrolysis in some ways, but is very different because it's you have the decompressive steps, which has an entropic benefit, and you also remove any volatilizable components rapidly. So it's in that kind of great menu of different techniques, it works slightly differently. And in fact, we do sell pyrolysis ovens ourselves, so it's just a different technology for a different thing. And finally, you have the thermo-oxidative mechanism, which can enable cleanliness and of any kind of composite materials, or it can enable a different route, different chemistry for different materials as well. And those pressure swings just enhance that every time. Fundamentally, our technology is patented via the process and not the materials themselves. So mechanically, it's a very simple piece of equipment. You make steam, high pressure steam. You then pass it over superheaters, which are essentially just a kettle for steam, a mechanical solution. And then you put it into a pressure vessel. And this is where the brains and 20 years of knowledge comes in, where we introduce those pressure cycles. We can pressurize and depressurize at our will repeatedly. And at the moment, our vessels kind of look on this vertical vessel. We have partners that have horizontal vessels. You can have whatever vessel size and shape you want, so long as it holds pressure, really. So a variety of feedstocks you can be put in. And then, moreover, you can collect that from the pressure swing. Our gaseous material comes out. Any monomers, any volatilizable material can then be condensed, separated off, and used. So our first example is an Innovate UK Smart grant called Emphasizing. With all the partners, some of you might be able to see, some of you not. And this is where it's a manufacturing project using recycled material. Longworth were the project managers, but we're sourcing the feedstocks and creating the recycled glass. And this is from the kind of early generations of wind turbine, from come offline, so end of life, bottom of the barrel, can't do anything with it. And we took this, we managed to recover the glass fibres from really messy feedstocks with all sorts of wood, all sorts of carbon fibre, rubber, copper, etc., etc. Then we passed it to our partners at Gen 2 Planck, which then chopped and resized this material at scale. From there, we've looked at various chemistries and sizing chemistries to make these glass fibres useful again, and I'll show you why you need to resize the material afterwards. Then, with Ford and Stamp, we have put this into a Ford Camberlink structural part to show that we can actually use recycled feedstock. We can use the worst recycled feedstock to create a valuable material. So we can depolymerize the resin and create that valuable material. So we're just looking on the left-hand side now. And so through about a year's worth of work, we've come up with a severity of treatment where we can convolute the temperature, pressure, and time variables to quantify the severity of how hard you hit that material. And as you can see, these wind blades were full of wood. They were epoxy-based resins. And if you hit at too low severity, you're going to get some depolymerization, you're going to get some char formation. But if you push that further up, you can find a spot. So there's a lot of room for optimization. And TWI verified that this was cleaner than virgin. Well, what does that mean? The sizing, the coating that allows the fiber to bond with the resin was removed. So we can start again. We can have a new application and we can size it for what we want. So in this case, we've gone from an epoxy to a virgin fiber to a thermoplastic nylon. Also, what was out of scope, we found in that aqueous recyclate we were forming a large amount of bisphenol A. So this kind of put us onto a mission of, okay, well, what's actually happening here? And we know that there's a temperature-independent pathway in thermolysis of different materials, and we believe that this is a really interesting case of actually, because we're operating at kind of lower temperatures than you'd expect for thermolytic degradation, that we can have a chance to recover those monomers from thermosets, which traditionally may not have happened. And so far, we've shown that we can recompound this material after resizing, we can put it up to 50%, and we can also show that our get a tensile benefit of including this material. Naturally, glass fibres can be quite sensitive to heat. So we are reducing the temperature compared to some other methods. And so while we get some knockdown, it's less than you'd expect. So this is an example of how we envision the future of decon, where we have both composite materials, fibre, be it carbon, be it glass, be it others. And then we have resin recovery. May that be thermoplastic, where we're melting the material off and separating that way, or depolymerisation. And just to show the breadth of this, you might think, okay, well, that's great and all, but when you hydrolyse something, it's going to break down and become useless. In the previous talk here, we talked about how melt flow index is a problem. Well, actually, this example shows we're on the steps to kind of change our levers of temperature and pressure to improve this. So this is some work we did with Ruby Moon and some various European labs on the Galactica project, where we took nylon, we took elastane, and because elastane is more hydrolytically sensitive, we're able to change our temperature and pressure variables to retain the majority of the qualities of the nylon while degrading and separating the elastane. And in this example, we were able to extrude it. This was with virgin, but subsequent projects have kind of allowed full reuse, but also operate at 42% saving. And that was including the separating sorting, which actually took up the majority of the LCA. And as our final example of this is use of hydrolysis and TPA recovery. So as I said, one side of our business is component cleaning. We have polyester filters, absolutely caked, and we clean them perfectly, and we have done for many years. But just to show you, we can take that terephthalic acid, we don't even need to purify it in many cases, and some work with Scott Barder, who I'll thank immensely in this, we're able to take that terephthalic acid and use it straight away. In some cases, they'd also performed some acid-based purifications, but also they were able to get a 33 recycled content in an unsaturated polyester. And we think this is a really interesting use case because that was waste to us. That was a production waste. We had to pay to get rid of it. And in this case, it's been able to be directly introduced. So when we talk about cost, when we talk about ease of recovery, we see decon as a core part of the future recycling strategy because you just need water, you just need electricity. And we're doing some fantastic work with partners. I would like to shout out Joe Pennell-Smith for some fantastic work as well that he's done with the company. But we just want to show you that recycled material can be good, we can have it easy, and we can have a wide breadth of polymers. So from a Longworth perspective, we've scaled up. We've made over 400 kilos of better than virgin, cleaner than virgin glass fibre so far, and we want to go further. We want to look at higher capacities and go to that next level. And I invite you all to have any conversations afterwards if you do so fit. So thank you for listening, and I'll answer questions afterwards.
As is standard for our...
What pressure you run at?
You could ask. The pattern is up to 15 bar.
I'm sorry?
Pattern is up to 15 bar.
15?
Yes.
1.5?
1.5. But we can operate in a wide range of spaces.
Maybe something for discussion at the end rather than now.
You use a catalyst from Europe?
No,
Thank you. Discussion at the end, but Charlie, straight over to you.
Right, am I pressing one of those?
I don't know if that's working actually. Yeah, there you
go. Okay, great. Thank you, Mr. Chairman. Good morning, everybody. It's a pleasure to be here. This is a slight change from my usual auditorium of a rugby club or village hall where I normally do my public speaking. But anyway, pleasure to be here. I'm Charlie Breese. I'm the Managing Director of Sylatech, and I'm going to talk to you today about a microwave pyrolysis solution to post-consumer plastic waste. I don't have a long speech, you'll be delighted to hear, and I'm intentionally not making this a fiercely technical presentation because we'd go on for weeks. But I'm going to talk to you today about Sylatech, its heritage, and our recycling ambitions. I'll talk you through our microwave expertise and its relevance to pyrolysis. I'll show you how we fit into the value chain, a quick look through our process, and then I'm going to finish with some details around our next steps and the timetable that we're operating to. So Sylatech was set up in 1964 in North Yorkshire, and this year we celebrated our 60th year in business. In fact, we celebrated on Friday night, which was quite a good night. Anyway, for those of you that don't know, the average life expectancy of a UK business is 8.6 years, so to get to 60 odd, I think is a pretty good achievement. We have 135 members in the team and are working on our site, and they operate in the 4 business units that we work in. We are a diverse business, for those of you that don't know us or haven't yet managed to see the website. The core business was a lost wax investment casting foundry, and we started the business by making microwave cast bends, which are the conduits for microwave energy. So this is what we were founded on 60 years ago. We soon added an integrated machine shop to machine the castings that we were making in the foundry, and this now also produces machined from solid parts that go into our microwave assemblies and sub-assemblies. Then we created a microwave business to penetrate further into that global market, somewhere beyond just cast bends, and since then we've added things like design, simulation, and many, many other processes that complement it, which make us a largely integrated business, vertically integrated business, sorry. Our fourth sector is R&D. We are passionate innovators. Our business was created by an inventor, mostly referred to as a mad inventor, and the theme still runs through our business today. We've always invested heavily in R&D. Most people with a financial head would say that we invest far too heavily in R&D, but we have always worked towards making a difference. This is an ethical objective of our company shareholders and is the basis of our interest in contributing to sustainability. As you can see on the logos at the bottom, we've got some blue chip customers, and we're operating in multiple sectors, but largely in the aerospace, defence and space sectors. So microwaves, this is a sort of a key slide because I need to stress our credibility in this area as it forms the crux of our entire project. Sylatech does microwaves. It's what we do every single day, day in and day out. We are designers of microwave bespoke solutions from the start to the end. We also do design and build to print, and this project really is a result of our innovative, design-centric mindset. As you can see, the applications shown on the screen where we operate are plentiful and they're relevant. So we are confident that we have the skills to deliver. We are using microwaves energy to induce pyrolysis, essentially breaking down the chemical bonds in polyolefin materials. But please be clear, this is not normal microwave oven or standard microwave activity. We have overcome the limitations of standard microwave heating, and I'll give you a bit more detail on this shortly. I think we all really know the problem. The linear economy does not provide the solution. In fact, it is the very essence of the problem. And as we also know, the numbers are just huge. Over 30 million tonnes of film and flexibles are collected in Europe alone, of which 23 million tonnes is either burnt or sent to landfill. Microwave pyrolysis can address this core problem and provide a solution to the demands which are coming in from far and wide. So we believe we are problem solving here. We're helping manufacturers get recycled content back into the production, especially for contact grade materials, as an example, food, medicine, where mechanically recycled materials can be problematic. We're supporting brands to achieve their pledges, and these are not insignificant pledges. A couple of the big names there. Unilever have pledged 25% recycled content in their packaging by 2025, and Nestlé 30% by the same date. These are fantastic starts, but I think, as we all know, increasing these numbers, and they will increase, will be a challenge due to the lack of available recycled material. So we provide also an outlet for the waste handlers, closing the loop on films and flexibles, getting ready for the 2027 Simpler Recycling Scheme. And let's not forget our consumers, who are getting ever more focused on their social responsibilities. As I said before, the current process is very linear. Currently, only 11% of local authorities collect post-consumer films and flexibles at the curbside. And unbelievably, that number has been decreasing for the last 7 years. But obviously this is going to change in 2027. A large majority of household waste ends up in black bags, which goes to the incinerators or to landfill. If you look at the model here, Waste handlers on the left are looking to reduce the amount of plastic sent for landfill. Petrochems on the right are looking to supplement traditional fossil feedstocks with recycled material. Sylatech and its process can fit neatly in the middle of the two, moving the economy out of linear into a more circular process. This model is fairly well known. It's what others are doing with various different depolymerizing technologies. So from our collaboration with waste handlers and with petrochems, we know that the model can and will work. Just please note the purification step in this model. It is not in the Sylatech box. This is a strategic decision. We do not want to duplicate the infrastructure and knowledge that is already existing with the petrochems, which is very specialist and very capital intensive. So following on from the previous slide, just a little bit about our conversion process. Starting step 1, we will do minimal pre-processing. Our target is moisture reduction. It takes a lot of energy to remove moisture in the pyrolysis process. In step 2, our revolutionary process, which is patent pending, is optimized for energy efficiency, hence moisture reduction being key. And as I said earlier, this is not standard microwave stuff. So we all have a microwave oven at home. You get your hot and cold spots like everyone else, which is why you stick it on a spinning plate. We don't do this. We're going to do it differently. We have developed a uniform heating process that improves the consistency of the oil that we produce. But for obvious reasons, I can't tell you too much about that today, and certainly not on this stage. There will also be a small percentage of char, which is neatly removed from our system, and that will initially be treated as a waste until we find an R&D solution to valorize it. We will generate non-upgraded pyrolysis oil, and that ties into our strategic decision not to purify, as I mentioned on the previous slide. In the final step, the excess gas is used to preheat the feedstock, removing the moisture, and we'll use any balance for combined heat and power to operate the system. As I mentioned, the key driver for us is efficiency, and we are aiming to be the most energy efficient system on the market for converting waste plastic films and flexibles. Our entirely targeted reaction overcomes transfer energy limitations of heating large volumes of low thermal conductivity plastic. Because of the uniform application of energy, we can get a more consistent and homogeneous product, which is how we get a better yield. It also produces a gas suitable for the system preheating and energy, as I mentioned a moment ago. Microwaves are instantaneous, and that enables a very tight control of the feedstock, control of the process, which accommodates a variable feedstock. I think we all know that feedstock from MRFs is inherently variable, and we've developed the product specification and the process to accommodate this variability. And because the system is so modular, it has inbuilt redundancy, which protects the whole system shutdown in the event of a small problem or a localized issue. In terms of the development roadmap, that's about as simple as you can keep a roadmap. Where we are now, we are here, we've got proof of concept, we've been working through this for 4 years, and we've been supported by 2 Innovate grants, with Sylatech providing all of the know-how and skills and the balancing funds. In early 2026, we want to complete an industrial prototype to run this continuously, validate it, and then move on to the first production model in late 2027. In terms of scales, just to give you some sort of perspective, our proof of concept is approximately 50 tonnes per annum. The prototype model is 500 tonnes per annum, and the main production unit is designed to be around about 5,000 tonnes per annum. Once we get to the production model, they'll be paired up into a dual to make a 10,000 tonne per annum, benefiting from some of the economies of scale that you can get. Some may question, why are we doing a prototype model? Well, it's a good question. It's a little bit like what Brooke said. Going from small scale to big scale, 50 tonnes to 5,000 tonnes, is a big step. And it's difficult to be a credible step. So we're doing this to get credibility, to move to main production funding in a more structured and believable manner. And then also, when actually it's completed, the prototype will provide a fully functional R&D unit where we can carry on further works to optimize our process. So in summary, I've just talked you through who we are, our microwave experience. Hopefully you can now believe that we have the microwave expertise. and why we're doing what we're doing. It's been a long, interesting, challenging, ugly, hairy journey most of the time, but actually it's been amazing, but there does remain an awful lot to do. To summarise our most salient points, our ambitions are to close the loop for all plastics, in particular post-consumer films and flexibles, enable regulatory compliance with recycled content targets, and create the most energy-efficient system for converting this troublesome feedstock. Our next steps are to raise funds, secure appropriate facilities with full environmental compliance before building the industrial prototype and then moving to full-scale production in 27. For those interested, we'll be launching our fundraising campaign at the start of January next year, when our pitch deck will be released, and we'll be looking for pre-Series A investment. And that's about it, really. Sounds fairly straightforward and easy. In closing, and in seriously, I'd like to just thank Sally Becken for her continued support, her knowledge, and her extensive energy, as well as her extensive contact book, and to thank Innovate for supporting us through our journey, not only from a funding perspective, but from the follow-on support that we get through Innovate UK Business Growth Team. So that's about it. Thank you for listening. I hope you found this interesting. There are three of us here today. I've got Gordon Gunn and Graham Sellers, who are full-time on the project with me, and feel free to come and see us afterwards if you've got any questions. Thank you very much.
Thank you, Charlie. Some more interesting points raised there. I'll hand straight over to Bushra, Al-Duri, for our final presentation of this session.
Thank you very much, Andrew. Good morning, everybody. My name is Bushra Al-Duri, and I am professor at the University of Birmingham. And we are in partnership with Stopford Limited, working on a technology called Solvergy, which is what I'm going to talk to you about today. And it's based on hydrothermal degradation of end-of-life plastics to produce value-added chemicals. I present you Solvergy is a technology that is actually based on hydrothermal degradation. In other words, it is based on degrading plastics in hot compressed waters. So the temperature and pressure of the hot compressed water are key issues in order to degrade these plastics. It is a green technology because by the chemistry of water, there is no emissions. No toxic emissions that come out of this process. So I will talk a little bit more about it. Actually, my approach looks like it's in parallel with the approach of the speaker before me, Charlie, in the sense that he's showing you where actually our technology falls. Our technology is situated between the plastic waste producers and the plastic manufacturers. So basically, what we aim to do is to convert difficult to break down plastics, especially polyolefins, into compounds that are prime material feedstock to produce new plastic. And these prime materials are what we call the naphtha range oils and the diesel range oils. Between C5 and C12 gives you naphtha, C12 to C18 gives you diesel range. This is based on petrochemical classification of oils. What is special about this technology is actually it replaces incineration, it replaces landfill, it is a green technology, and it requires reduced number of processing steps. So by this, it actually, as I said, it replaces these two existing disposal methods. They are not recycling methods, and it outperforms pyrolysis. Having said that, as a chemical engineer, I do not believe that there is one perfect process for everything. The market has, and the need actually needs many processes, and all of them are, some of them are emerging, some of them are ahead of others. So as you can see here, Solvergy gives you, it has been shown, and that I'm talking on laboratory scale, it has been shown that it gives about 90% oil yield, very little gases, and very little chars. Everybody in this room knows the problem of plastics, and everybody knows that the countries are in race to actually trying to reduce their wastes either by reuse or by recycling. Also, in order to come out with a new technology, not only should it be, as we all know, scientifically advantageous, you will have to also convince the businessman to invest in it, and you have also to convince the government that it fits with their policies. So it is never easy, and there is always a question of balancing all these factors. So what makes Solvergy interesting or worth thinking about and talking is actually it targets non-recyclable wastes. When I say non-recyclable, the ones that you cannot break down by hydrolysis. The second thing also, it actually handles mixed waste. It handles contaminants. So you don't need to remove the contaminants, you don't need to clean it, it can use it as it is. Also, it enables oil recovery, and it yields compounds, as I said to you, that are suitable precursors to produce new plastics. Or you can also use them to produce fuels. But our work, we target plastic packaging material. And as I said, because it is an eco-friendly process, it has very low carbon emissions or non-carbon emissions. Now, what is the technology? The technology is based on the special properties of water above its critical point. Just a very quick explanation. A critical point is a characteristic point of every material, especially fluids. Like we have the melting point, we have the boiling point, and then we have the critical point. The critical, above that, water has a different chemistry from the water that we know. It no longer dissolves salts. In fact, it dissolves all organic materials, including polymers. And this is the basis of this technology, which we call supercritical fluid technology. My specialty is in water. I've been working on that for almost 20 years. I've used it in wastewater treatment, breaking down, and now we're applying it for degradation in the plastic industry, or plastic molecules. So that is exactly what I said, and the beauty of it, again, the chemistry of water pushes the reaction in a certain direction that goes more towards the desirable products than other process that haphazardly breaks down the molecules into smaller units. Of course, this comes at a cost and at a price. You have to work at a temperature, at a pressure as high as 250 atmospheres or 250 bars, because it has to be above the critical pressure, and at a temperature above 375. The process itself, I put it here qualitatively as opposed to putting a diagram. The plastic preparation and the plastic conversion are the two key processes that need deep research. The aim of plastic preparation is you actually, our ultimate goal is to make it a continuous process, not a batch process. So you have to prepare the plastic in a way so that it can be flowing from one component to another. And because it's based on water, there is no drying. You know, it is actually suspended in water. You put it in water, and the water, with its heat and pressure, it breaks down the molecules. So this is the first step, and then the conversion, this is where the product is produced. As you can imagine, you come out of this step with highly pressurized, very hot stream. So heat recovery and integration is key to make it economically feasible and energy positive, if you like. And then finally, product separation and purification. When I say these two steps are the most important, what I mean is this is a simple step. So once you produce it, there isn't so much downstream processing. It becomes simple in terms of chemical engineering, simple separation. Now, our work started in 2019 to 2020. In fact, we got the first study in techno-economic feasibility study. And then that followed into the first time we created a unit, and we are working with polypropylene, low-density polyethylene, their mixtures, and also we have tested real wastes. Our studies are in 3 stages. We've done investigations in just 25 mil reactor, just to prove that things can happen, and then we moved to a stirred 100 mil reactor, and then in the summer we finally tested and built a continuous, or if you like, a semi-continuous facility, which is what I am saying here. The prototype is designed, commissioned, and it is trialed, it is actually tested at Birmingham Energy Innovation Center in Paisley. That's me, by the way, and this is my postdoc, Dr. Rafael Orozco. Now, what do we do? When we do the experiment, we get the product. So let me just step one step further and then come back to this. Now, if you can see here, we get the oil, the product, and the water below it. Now, this product, we need to analyze it and see what type of oils, what components are in the oil. And this is what we do. I'll go back up to this. What we do is we do TGA analysis based on the oil chart, the crude distillate chart, because my background, by the way, is in chemical engineering, but I also lecture in petroleum refining. So this is what I used, my experience in terms of when you analyze the oil, these are the components that we have been getting. This is the carbon chain length, and these are their boiling points. So when you do TGA analysis, they come out successively, and then you can actually evaluate what are your products. Now, the products of interest, or if you like, what the consumer wants, what the people who purchase the product want, is these first four, up to here. So kerosene is very much close to diesel in terms of boiling point, and light gas oil is also close to diesel. Actually, this should have been 13 to 17. No matter how much you revise, there is always a typo. Okay, now this is hydrocracking of polypropylene. So as you can see here, this is 3 different temperatures. Sorry, a certain temperature, 3 different reaction times. Now, this is the first, these are the ones that they are all below the boiling point of 321. As you can see, we have got, if we look at set condition 3, we have over 40% of heavy naphtha, over 40% kerosene, light gas oil, and atmospheric gas oil. So these are the ones, if you add them up, they come up to more than 80%. This work was done in the 25 mil reactor. Now, LDPE, sorry, I went down, up. Yeah, LDPE is quite tough. LDPE is very, very hard to break, and it needs more than PP. And therefore, this is, again, this is our studies, and these are our analysis. And as you can see, for example, here, nearly 35% of kerosene, about 20% light gas oil, 18% heavy naphtha. If you add them up, again, they give you a very good sum of what the product is expected to be. This is both mixed together. What we can see from here, this is PP, this is LDPE, and this is PP. So there is more PP than LDPE, obviously, because as I said to you, PP is easier to break. However, when we mix them, we saw that the mixture enhances the slow burner. You know, the mixture enhances the slow one, and improves, so as if the components egg each other. I have seen actually this phenomena in other technologies and other processes. Science is the same, dressed in a different way. You know, the harmony of the universe is the same, but it takes different shapes all the time. Now, just to show you, this is the University of Birmingham, sorry, the BAKE, the Birmingham Energy Innovation Center. This is our test facility. Now, this is the continuous one, as I told you about. This is the pre-treatment vessel. It's actually, we call it, we have a nickname for it, the Beast, because it is massive. And we went through a lot of safety tests before we operate it, and it works great. And this is the oven where the reactor sits. After that, then, so this is where the pre-treatment happens. This is where the breakdown, the full breakdown happens. And then it comes out and it goes into pressure reduction. And then, I mean, this does not have heat recovery. Heat recovery is for the future, because in a small scale, heat recovery doesn't pay. We are in partnership with Stopford Limited, and what we do is our work goes, it's a little bit unusual. I mean, I'm the scientist, I'm the inventor of the technology, if you like. We produce data, and then this data goes to Stopford, that they do the scale-up calculations and the scale-up the design. So they are like a mixture in between academia and the end user. I'll come to our next step. So, but in parallel, as we produce that, I also have a team of people who work in the detailed, you need modeling, you need kinetics, the detailed science. So there's in parallel detailed science work and this data that goes to Stopford. So as you can see, what they do there is process flow diagram, mass and heat balance, process scale up, IPR strategy, conceptual plate design, finance modeling, life cycle assessment. This is what they do while we do the science and the technology. This is just a quick plant layout. Theoretical, of course, we don't have a plant yet. Again, this is like imaginary. This is how it might look like. In addition to now pipeline applications, we also work on PET, polyethylene terephthalate, on a different project, and this is on neutral hydrolysis of PET to produce high purity terephthalic acid and ethylene glycol. The interest of the project is the terephthalic acid. Many people talked about PET before. PET can be hydrolyzed. PP and PE cannot be hydrolyzed, probably chemically speaking, because PET was formed by combining two molecules and subtracting water, a molecule of water. That is why when you hydrolyze it, you give the water, it takes back its place and breaks it down. PP don't have this. That is why you cannot hydrolyze it. Also, we have a new project now in collaboration with Magorion in Singapore. And what they want to do is actually, they produce bitumen, but they want green bitumen produced from wastes, and the waste is actually a mixture of MSW, municipal solid waste, and plastics. So we are in collaboration with them. It's just at the beginning, this project. And basically month one. So the structure of our work, we, University of Birmingham, are with a license agreement with Stopford as the Solvergy team, and Stopford sub-licenses IP contract. In other words, if we want to go further, they would be the first port of call. This technology has created, this is the team, people from Stopford and from Birmingham. And we have started, as I said, with techno-economic feasibility study, and then 3.5 tons per annum test facility and scale up. This has been done now, and now we are at this stage. We hope that we continue, and of course, We always need investment on our journey, and we need more and more funds. There has been a lot of media coverage, which as much as I like, I am careful about. As a scientist, when you advertise something, you don't just advertise, you have to actually, you know, when you talk to an industrialist, he wants to see it in towns, he doesn't want to see it and stuff like that. So I am always very careful in talking about it, but it's nice to get attention, right? I would really like to thank Innovate UK, because without them, none of this would have happened. So, and I also thank Sally Becken for giving us the opportunity today to talk about our technology, and thank you for listening. For more information, this is my email, and Dr. Ben Herbert, who is director in Stopford. Also, we have poster number 7, where my student Luqman is actually talking a little bit more in technical if anyone wants. Thank you very much.
Great, thank you to our speakers. Some really interesting information and talks about the different technologies they're working on in this area. I'm very happy to open the floor if there are any questions that people want to get us rolling the discussion with. Oh, thank you.
Can I ask a question for Professor Al-Duri? In your liquid products, your oils, what was the olefin paraffin ratio?
Pardon?
What was the ratio of olefinic material to paraffinic?
We haven't done any GCMS yet, but you mean olefin to paraffin? It is mostly paraffin, very little olefin. I remember now we have done one study in a GCMS library, and I would say the olefin was no more than about 2.5 or 3%. I have the graph here, and mostly paraffin and some aromatics. Did I answer your question?
Yeah, please.
I missed most of that. I look forward to seeing the presentation. I'm annoyed session I want to see most of it. What do we have to do for this technology group to deploy into plastics as part of the solution to overcome this terrible press that I think pyrolysis and other technologies are getting, it being high carbon? Now, there are examples and applications that are, but we need this depolymerisation, this recreation of chemistry. What do we need to do to smarten up and present the right statistics and metrics in terms of carbon management and environmental performance?
It's an excellent, it's one of my questions, but better phrased. Does anyone want to come in on that?
I can make a quick comment. I think we last week said about awareness. So as long as anything to do with depolymerisation, the emissions are reduced compared to incineration, it'll always be good. As long as incineration is as bad as it is, let's say, it'll always be the awareness. Just making people in public aware there is a need to straight off the bat.
Yes, I mean, can I take it from we need to generate awareness, because as I was talking about this, Innovate UK have been funding steps. However, to move to the next step, we need investors. In other words, we need people to know about it so they become part of the journey. I understand an investor doesn't give you $1 million if he doesn't know what is it. You know, what is it you're going to do with it? Hello?
Just keep talking, Bushra.
Yes, is that clear now? Yes, the thing is, we have to have investors that buy into the technology. We need fund that actually buys into our technologies. And where they come, where these funds come is very crucial. First comes the research fund as an EPSRC, and then comes the Innovate UK fund. In my case, and I am very sad to say, I had very little success with EPSRC, but Innovate UK have given us great support. Without them, we couldn't have. But that is why we're trying to do both at the same time. We do the fundamental and we do the applied research at the same time. Now, from the applied to the slightly more applied, the demo scale, you need people to buy into that. Otherwise, it will always stay in the research level and nothing will happen.
James, Charlie, any thoughts on that from a different point of view?
Yeah, I mean, I echo this, the sentiments entirely. The difficulty we see it is you get funding to go to a certain level, as you've alluded to, and then there's this sort of large chasm of void where you've got to go out to industry, and you need to become professional fundraisers to try to take on this technology and get it to scale. So, you know, you have these innovative ideas, you've got some fantastic things, but there is only a finite amount of money. So where I would say, and it's mission impossible, I would suggest, is that government really needs to understand the difficulty of bringing these new technologies to market and getting them to scale. Because you can get so far, but it is such a colossal leap from in my case, 50 tonnes per annum to a 5,000 tonne per annum. You know, I'm a £10 million business, and that could be a £1 billion business if we got it right. But how on earth do companies like us get the support to get it to scale? So,
I would say it's quite an emotive series of languages and words that we see in the industry. If I look at the composite space, we see that kind of a lot of the manufacturers who want to reduce their offcuts and waste, the demand is coming from theirs. And so we don't necessarily see the same pressures and kind of words of recycling. If we look at kind of where there's been successes, and there has been successes, things such as the FAND in Germany has worked quite well. And I think to get past that emotive and to change kind of end consumer behavior has to be done, and that has to be done from a top-down level. Now, I don't want to say landfill tax everything and kind of that is the way, but at the end of the day, these are kind of behavior changes that have to take over a long time, and they have to have more than a kind of parliamentary cycle to kind of be engaged, right? Because at the end of the day, money talks, but people are still going to throw it in their bin if it's convenient, right? We see this. So I think it's a combination of regulatory, but also public awareness and kind of depoliticizing a lot of the words that are bandied around in my case, I see quite often.
Don't we need buying from the plastics industry, the raw material manufacturing? This is really where it all starts. And I know, we've got BPF here. We really need all of these things done on scale. We can't run 5,000 and 10,000 plants and say we're going to solve the problem. We need plants running at the scale of manufacturing. So why do we have this hesitancy? The industry is staring at the precipice if they don't solve the problem, because they'll be regulated out of operation. So we really need mass movement. I mean, it's great to see the innovation happen, but then adoption has to be at the scale at which we're producing material on a short-term basis, and we've got to close the loop on it.
100%. I feel that we've had over 100 years of making these processes more efficient, right? And so we're starting at a different point to incentivize it. I really do feel that investment upstream, traditionally the end person pays for it, right? So, you pay your council tax, you kind of don't expect anything further. The further you go upstream, if you go to those commodity chemicals, then I feel like that's where the largest economies of scale are. And I personally, from a Longworth perspective, we see not just polymer users and polymer producers, but kind of going back further, that is a really real key area for kind of scaling up and putting that investment in. And we see interest as well.
We can't have the disconnect between making material, giving it to the consumer through the supply chain, saying, well, we've done our bit, sorry, you sort it out. Consumers can't sort it out, councils can't sort it out, the innovators can't sort it out, they can provide the technology. It's then has to, you then have to take back the close the loop. So really, the concept of extending the user responsibility has to be brought into practice. We keep talking about it, but we need to take it into a stage where it's adopted. And at the moment we see the conflict between recyclers and virgin producers, one undercutting the other, destabilising, and things that all happen that happen. One's trying to solve a problem, the other one's creating, and then we're undercutting that solution. This is where we are right now. This is why recycling is starting.
Yeah.
I don't know if you've noticed, but there's about 110 nodding heads there. Everybody agrees with you. And it's probably one of the biggest challenges. We 15, 20 years ago, everyone was panicking about how we recycle paper, plastics and such like. We're 20 years behind, the groove. We've been abusing plastic ever since the day it was generated and created. And we are horribly behind this technology. Europe is in front of us in terms of collections, but the technology globally is still quite third world in comparison to where lots of these other recycling things, metals and such like are. Unfortunately, so much of it is done across boardroom tables and behind the closed curtains of Whitehall and such like, and that's why it makes it really difficult. But what you're saying is right. I wholeheartedly agree. It is a challenge, and which is why we're not seeing massive rollout of hugely successful recycling plastics going on right now. It is incredibly difficult, and every force appears to be working against you, which is why you don't see the successes in the market that we really want to see.
Can I follow up to the panel with that question? Please
Can
feel free
I
to
just
continue answering Ed's
say,
question.
yeah.
But what do you think, is the technology gaps? Is it policy direction? Is it feedstock provision? What of those, I'm suspecting the answer is going to be all of these needs to change, right? But in your opinion, as the panel, people really in this, what do you think are the really big drivers that are going to unlock the massive change that we all want to see in this area? You've got the microphone.
So, yeah, no. So I kind of sit on the enzymatic biorecycling, which kind of works in a similar theoretical way, but completely different. So kind of leading on to what you were saying about the polymers and the plastic manufacturers. For me in particular, the polymer design is quite important. If you guys could make a polymer which can make our enzymes be able to break it down faster, and we also can have an enzyme which is really good, it works together. There is also an element of trust and transparency. So I think from our kind of enzymatic recycling prospect, we're kind of a few steps ahead. So we now have got that pilot plant coming through. But the whole process has been built by collaboration through industry. So it's no longer just have a theory, have an idea in academia and suddenly jumping up to scale up. You have to have that connection first with industry before you even get to the point at the end. Because if you have a great process, but once you step forward out of academia and you go into industry, they say, hang on a second, that won't work. The plant won't have that big of a facility, or that metal can't be next to that chemical. You have to have the industry partners to tell you that early on in the process development. Otherwise, it's never going to reach a large scale kind of area. I think, last thing I'll pass over, with our technology, so the TRL, you can have fantastic, you can be ready to go. But I said about the feedstock, you need to have the feedstock coming in. And obviously where policy implemented that fact of including rPET into some plastic products, yes, that saw a massive demand for recycled PET, which then had a knock-on effects, which some are good, some are not so great, but at least that implemented change. So I am kind of now sitting more on the policy side, because you have to have the pressure put on the big companies to actually choose alternatives. So I'm funded by Coca-Cola bottling, so the Hellenic side. And the only reason they kind of looked into this industry was because they realized that they had to have an ulterior way of producing rPET internally, rather just through mechanical processing, because they need the outputs, which is TPA, which is valuable. So you need the large companies to have that pressure. So yes, I'd say feedstock policy and pressure, so all of it.
Okay, to answer your question, Andrew, I personally think it's the policy. Like when they put, for example, wrap, that all recyclable plastic has to be, we cannot use use plastic by year such and such. When they put deadlines on plastic use, on climate change, whatever it is, they put deadlines. These are not based on how long it takes to produce new technology. So if you really want the countries to meet the deadlines, then you need to open the door for more research, i.e. direct the funding more towards research, and then the researchers will produce something that will give industrialists something to hold on to. Because you cannot just give them theory, you need to give them something they believe into and use. I mean, it sounds maybe ideal, but it starts from the top to make the fundamental work go, and then the middle people will then see results and believe in it, and then these people will convince the industry. You know what I mean? That's my opinion, anyway. A very humble opinion.
Thank you, Bushra. It's like I've paid you, because that's our time is up, unfortunately, for this session. My tummy is grumbling as well. But it does link beautifully for me to remind you, if you're interested in UK plastics policy around sustainable plastics and recycling, we've got lots of interesting recommendations in this document, and a little stand outside, so we welcome you to come and talk to us. But please join me in thanking our excellent speakers, and thank you for your discussion.